Hello and welcome to our introductory module into organic reactions. So today, before we go into the different type of organic reactions for each class of functional group, we're going to be going over the different types of reactions in general that you're going to come across, and then at the very end, how to tell what products you have at the end of these reactions. So the first type of reaction we have is a reduction reaction. These reduction reactions are a bit different to the reduction reactions you may have come across in your study of electrochemical or galvanic cells. Now, essentially, in simple terms, it is when a hydrogen is added across a double bond, and especially in an alkene. They happen also in amines and to a lesser extent in an alkyne. The official definition, however, of a reduction reaction is a decrease in the number of carbon to heteroatom bonds and an increase in the number of carbon to hydrogen bonds. Recall that a heteroatom is any organic element that isn't carbon or hydrogen. So that could be oxygen, nitrogen, so on and so forth. It is important to understand this definition, the official one that is, and it will become relevant in a couple of slides' time. However, I want you to just get a simple appreciation with this simple reduction reaction that I have here. So I have ethene and I have hydrogen. I'm going to break up this hydrogen and just make it look like this. I should also tell you that these reactions usually require a catalyst and a large amount of energy to occur. So a catalyst and a large amount of energy would result in this bond breaking, giving you an electron on either side, and also this bond breaking, creating two hydrogen free radicals. These hydrogen free radicals can then attack the lone electrons on either side, and thus ethene becomes ethane. Oxidation reactions, however, are the complete opposite. So they result in an increase in the number of carbon to heteroatom bonds, whereas reduction results in a decrease in the number of carbon to heteroatom bonds. Oxidation reactions also result in a decrease in the number of carbon to hydrogen bonds, whereas a reduction reaction results in an increase in the number of carbon to hydrogen bonds. So I wouldn't worry too much about this just yet. We have a slide covering this. I just want you to appreciate that an oxidation reaction is essentially the opposite of a reduction reaction. So we're going to be going over the slide in more depth in a couple of videos' time and breaking down each class of compound. But for this slide, I just want you to understand the basics of an oxidation reaction. So if we go from left to right, I have a primary alcohol. All I want you to observe is on the oxidation step, I'm losing a carbon-hydrogen bond. So I have the primary alcohol here. I have two carbon-hydrogen bonds, and then I go to 1 on the oxidation step, and I obviously get an aldehyde. And then if I do another oxidation reaction, I have no carbon-hydrogen bond, and now I get a carboxylic acid. Conversely, I could go the other way. So I start with the carboxylic acid, and I reduce it to get the aldehyde. So I gain a carbon-hydrogen bond, and then I can reduce it again to get the primary alcohol. In this way, similarly here, I've had two carbon-hydrogen bonds go to 1, and another high-yield association is, so you can actually go oxidation and reduction reactions in organic compounds can happen between alkanes and alkenes. So if you look at the carbons here, I'm going to draw some hydrogens in. Obviously, if we go from left to right, they've lost a hydrogen each, so it's an oxidation. If you go from right to left, it's a reduction reaction. Hopefully you understand why now. So essentially a condensation reaction is a reaction in which you have two molecules that react to form a larger molecule and water, and the key component is the water. So usually these will happen between two molecules with a OH bond. So that might be a carboxylic acid or an alcohol or two alcohols. That'll give you a condensation reaction. The key example for your senior studies is esterification. So esterification, don't need to understand it right now. Just understand condensation reactions. We'll have a separate video on it as well. Esterification is when you have a carboxylic acid combining with the alcohol. So these OH groups kind of combine together and they leave the O. So if you can imagine, this O stays, this H and that OH kind of combine, shoot off, and they give you the water. So obviously this water kind of is a key defining aspect of a condensation reaction. Thus, esterification is a condensation reaction.
So once again, don't really worry about the method, but an addition reaction is when you have a simple atom. Usually this is a double bond or a triple bond, and then you actually add another atom or the constituents of another molecule throughout that atom. So on the left-hand side, we have ethene, and on the right-hand side, we have hydrogen chloride. In some certain circumstances, it could actually give you this compound here, which is chloroethane. I like to pair elimination reactions and condensation reactions kind of together, because an elimination reaction can be the opposite of a condensation reaction. It doesn't have to be, so it can be. So an alcohol dehydration is a common example of an elimination reaction. It's when you start with a bigger molecule and you break down into smaller molecules, right? So here I have an alcohol. In the right circumstances, so if I reacted with strong H2SO4, don't worry about this just yet, it can give you ethene and the water molecule, right? However, its elimination reactions aren't just exclusively dehydration reactions. They're just, the definition is any reaction in which you start with a really large compound, you do something to it, and it breaks down into smaller compounds. So at the very basic level, a substitution reaction is one in which one atom replaces another. So in the case of an alkane, you have a free radical substitution. We'll go over another type of substitution in a couple of slides' time, but usually for an alkane, you just react it with chlorine or bromine gas, and I'll show you that reaction in the next slide. But the highest pseudo association is that it'll have like a one atom replacing another, and that will require a large amount of energy. Usually you have to supply this in the form of UV light. But this is that example of that substitution reaction. So I have a really simple methane molecule here, and I have chlorine gas. If reacted in this right circumstances, so lots of UV energy, this chlorine could potentially displace this hydrogen and give you chloromethane. So the second type of substitution reaction that you'll need to remember is the nucleophilic substitution that will happen in haloalkanes. So what does that actually mean? So the second dot point is something that I'm sure you're well accustomed to now, is that halogen atom is more electronegative than the carbon atom, and thus there's an unequal distribution of electrons, creating a difference in electron density. So the halogen atom will take on a slight negative charge and the carbon atom a slight positive charge. But what you don't know is a nucleophile. So a strong nucleophile, so think of nucleo, so nucleus, which has a positive charge, phile liking, so a nucleophile is positive charge liking. So a strong nucleophile will be extremely negatively charged. So a good example of this is the OH minus anion. So this, if you can think of like a tug of war, so carbon is bonded to a chloride, which is pretty electronegative. But in the right circumstances, if this OH minus attacks this bond, it will actually preferentially bond with the OH and kind of boot this chloride off. And there's a nice reaction in the next slide that kind of shows that. This is like a pretty classic reaction of a chloroalkane or a haloalkane reacting with sodium hydroxide to give you a primary alcohol. So we'll draw up some charges. So chloride will obviously have the slightly negative charge, carbon will have the slightly positive charge. I'm going to break up this sodium hydroxide, pretend that it's in solution. So I have this hydroxide anion. So what happens is this positive charge and this negative charge attract more than this deltas. These deltas do, and it's actually stronger than this bond here. So essentially what you'll get is, if I clear that, under the OH again, carbon will kind of make a bond with this, and this bond will weaken and kind of boot this off. So what you'll get is this primary alcohol and a chloride anion. Last but not least, it's probably the reaction that you're most comfortable with, and that's a combustion reaction. So the basic definition is a reaction where you have fuel, it reacts with oxygen, and you need that initial input of energy, whether that be a spark or something. The highest yield thing to remember is a complete combustion reaction is when you have a high amount of oxygen and the products are only carbon dioxide and water. So always remember, balance your equations. if it's incomplete, it means there's not enough oxygen for the fuel. So you get carbon dioxide, water, and carbon monoxide. That is the most important thing. So you get carbon monoxide as well. So it's all well and good knowing the different types of reactions, but it's equally as important to be able to test and find the compound that you've made when you take another compound through a reaction, right? So this table, we're going to be breaking it up. So over the next couple of videos, we're going to have reactions of alkanes, alkenes, alcohols, carboxylic acids, amine, amides, and esters bunched up into a couple of videos. So we'll be breaking up this video into the relevant sections, but this is probably the last time you're going to see it in its full form. So we'll just go through it very briefly. Bear in mind, you might not have the context. So with an alkane and alkene, so very briefly again, the main way to distinguish them is using bromine water. With alcohols, you can add some calcium chloride. It'll make a bit of hydrogen, and you can distinguish that with a pop test. If you've never done the pop test, essentially what that is that you trap the hydrogen into like a little test tube, get like a small lint, and it should make a loud audible pop. And that's just confirmatory for hydrogen. With carboxylic acids, adding sodium bicarbonate should generate CO2 gas. With amines and amides, it's a bit tricky. So with amines, they're slightly basic. So if you use universal indicator, you'll see a color change. If you want to distinguish an amine from an amide, you can just stick the universal indicator. If it changes color, it's probably an amine. If it doesn't change color, it's probably an amide. But the official confirmatory test for an amide is when you add sodium hydroxide, you'll get ammonia, and ammonia gas, that is. And then if you stick red litmus paper, it'll turn blue, because obviously ammonia gas or ammonia is a slightly weak base. With an ester, unfortunately, there's no official test. They just tend to have like this really nice perfume, fruity odor. People say it's fruity. I think it's more perfume-like. You'll see when you do the prac.